Hello everyone. In the previous class, we discussed some of the in situ tests for the determination of modulus of deformation of rock mass. So, today in this new week, we will start a new chapter which is on rock mass tunnel support interaction analysis. So, today we will learn few concepts related to rock mass tunnel support interaction and also learn about ground response and support reaction curves. The concept includes that what exactly do we mean by the rock mass and tunnel support interaction. So, for that we need to understand first the system. So, there is the existence of a mechanism of interaction between the rock mass and the support system. So, first if we talk about the support system, it can be rigid or it can be flexible. What do we mean by rigid support system? That means that its stiffness is going to be extremely high, but in case of the flexible support system, we have very low stiffness of the support. Now, since the stiffness of the support is very low, it is going to result into very high radial deformation, which we are representing by UR. And similarly, in case of the rigid support system, the stiffness being very high, so the radial deformation will be very low. Now, in case if we want to restrict the complete deformation of the excavation, then we have to provide extremely high stiff support system, which may not be that economical. And if we go for very flexible support system, then in that case the deformations are going to be very large, and in that case the system may fail because of the reason that the deformations are more than the permissible limits. So, what is the way out? So, here we need to choose the system having intermediate stiffness where you have Ks as well as the radial deformation being moderate in nature. So, we are not going to adopt two extreme cases, maybe the rigid or the flexible, but somewhere in between we have to use the optimum type of the support system so that it is neither too rigid nor too flexible. The question comes that what should be the magnitude of the permissible deformation. Then another thing which one needs to keep in mind, that for the system to be in equilibrium, there is a particular combination of pressure and deformation. So, the load which is imposed on the support system, it becomes the function of deformability characteristic of rock mass, and this deformability characteristic of the rock mass in turn becomes the function of the stiffness of the support system. See, this is how it can be explained, that whatever is the load that is imposed on the support system, it will be the function of deformability characteristic of the rock mass. Let us say if it is more deformable, then there is going to be more load which will be imposed on the support system. On the other hand, this deformability of the rock mass will be the function of the stiffness of the support system. So, if you have very rigid system where the stiffness is more, obviously the deformability will be low. And there comes the interaction into picture, which is the function of the stand up time. So, we have discussed what is the stand up time couple of times in some of our earlier classes. Now, before I go further, let us try to understand first the behavior of the rock mass and then behavior of the support system. Then we will try to understand their interaction phenomena. So, as far as the rock mass is concerned, its material behavior will be given by stress strain response, or we can call these as constitutive response of the rock mass. Any rock mass can behave in the linear elastic manner, which is a particular case of the solid competent rock. So, in case if you have the solid competent rock at the site, it is expected that it will show the linear elastic stress strain response. Similarly, one can have non-linear elastic stress strain response in the case of competent rock, but with lesser value of modulus as compared to this particular case, which is solid competent rock. In case if you have the incompetent rock, then one can observe non-linear inelastic stress strain response. In case of the jointed rock mass, one can have highly non-linear inelastic stress strain response, and some of the jointed rock mass, they also exhibit time dependent stress strain response. So, based upon what type of rock or rock mass that you have, accordingly their behavior can be either elastic or elastoplastic or viscoelastic or viscoplastic. So, this is about the behavior of the rock mass. So, now coming to the support system. So, there are various types of support system. We have discussed these earlier as well. So, let us see how on the type of the support system, how is going to be their behavior. So, as far as rock bolts are concerned, they exhibit tensile behavior and their response is elastic. In case of the shotcrete lining, they show elastic plastic response. Similar is for the concrete lining, but here it is elastic and brittle response. For the steel sets, it is elastic plastic, but it is ductile response. And in case if you have the combined support system, then it is going to show you the complex behavior. As far as the combined support systems are concerned, I mean you can have the combination of shotcrete lining along with the rock bolts. So, such combined systems fall under this category and they will have highly complex behavior. Now, let us combine the two, rock mass as well as the support system. So, this complete system has two components, as we have seen that it is excavation itself and the support system. Now, depending upon what type of rock mass it is, your excavation will show respective material behavior. Similarly, what type of the support system is needed, correspondingly you will have the mechanical behavior of the support system. Now, the tunnel as a structure which is excavated in rock or rock mass, and then the second one is the support system. Their behavior together is interdependent. In what sense? In the sense of their mechanical response. What do exactly we mean by that is that we are going to focus on pressure versus deformation characteristic of these two components. Take a look here. This is the excavation which is done maybe through rock or rock mass. The in situ stresses are considered to be hydrostatic. So, since it is hydrostatic, you see in all the direction it is acting and the magnitude remains the same. This is what is the excavated tunnel boundary, and then you allow some radial deformation to take place. So, this is how the radial deformation UR will be measured, that is from the excavated tunnel periphery, and then you have the support system. So, this is how our rock mass tunnel support system will look like. Coming to this radial deformation, it is elastic only in very good quality rock or rock mass. It occurs almost instantaneously for all the practical purposes in case if you have very good quality rock or rock mass. Then this radial deformation can also be elastoplastic. It can be time dependent but elastic if the magnitude of in situ stress is less than yield stress of rock or rock mass. In case of the incompetent rocks, rock mass with relatively higher value of RMR or Q, they fall under this category. Now, what happens if this in situ stress is more than the yield stress of the rock or rock mass? In that case, the radial deformation can also be time dependent but plastic. So, this is the condition when magnitude of in situ stress is greater than the yield stress of incompetent rock or poor quality rock mass. Then it may reach a constant value after some time and failure may not occur. So, the tunnel without any support system, it achieves the elastic equilibrium or it may reach a constant value after elapse of time and may attain the plastic equilibrium. The failure occurs in such case as the resultant deformation becomes more than the permissible deformation. So, this gives the indication of occurrence of failure. What should we do to prevent the failure of the tunnel? We should install the support system after certain amount of time. Now, why we should install the system after certain amount of time? Because if we apply the system immediately, there is going to be lot of support pressure onto the support system and we need to go for extremely rigid support system, and that may not be economical. So, we provide the support system after certain amount of time. What should be this time? This time is correlated with the stand up time of rock or rock mass and it should be known beforehand. It is a function of RMR or Q, which in a way showing you or telling you about the quality of the rock mass. So, in case you have low or very low stand up time for a particular type of rock or rock mass, in that case support system should be installed within the specified stand up time. Although this installation of the system should be always within the specified stand up time, but why we are mentioning with reference to low stand up time here is that sometimes you have seen that the stand up time can be as low as few hours after the excavation. So, there we should not wait for those many hours to get over, but then we should start the installation of the support system as soon as possible. What is the purpose of the support system? This is to arrest the continuing deformation of rock or rock mass, and therefore it becomes directly a function of stiffness of support system. So, the radial deformation is unrestrained before the installation of the support system, but then this radial deformation becomes restrained due to the stiffness of the support system after it has been installed. Now, if this radial deformation is to be restrained completely, this means that no further deformation of the support system is allowed after its installation. So, this required stiffness of the support system is the function of many parameters. These include magnitude of in situ stress, then size of the excavation, quality of rock or rock mass, time of the installation and the total time elapsed from the time of excavation. So, when we go for the design of the support system, all these factors should be accounted for. So, if you want to restrain the complete deformation, the required stiffness of the support system, which we are representing as Ks, is going to be quite high, and this will make the support system prohibitively uneconomical. So, to achieve the overall economy, one should go for the flexible support system instead of a rigid system. Now, what does this flexible system does? It permits some of the deformation of the rock mass tunnel support after the installation of the support system. And because the deformation is allowed, so the support system is to withstand a lesser amount of pressure or stresses. So, therefore, we do not need to provide that heavy reinforcement system or the support system. So, we can go for the flexible support system rather than a perfectly rigid system. The deformation of the support system, it is governed by the load transferred by the surrounding rock or rock mass. We all know that if larger loads are applied, the deformations are going to be more. So, basically the deformation will be governed by what is the load that is being transferred by the surrounding rock or rock mass. So, the load that is mobilized in the support system becomes the function of deformation of the surrounding rock, which itself is a function of stiffness of the support system. So, you see what exactly is happening here, that the stiffness of the support system is a function of deformation, and deformation is a function of the stiffness of the support system. So, this basically is resulting into the interdependent behavior, and we call this phenomena as the rock mass or rock tunnel support interaction. So, please understand that if somebody asks you that what do you mean by rock mass tunnel support interaction, you should not just say that, oh, it is their interdependent behavior. That is incomplete definition. Of course, when the term interaction is coming, it is going to be interdependent behavior. But what exactly do we mean by this interdependent behavior? That should be absolutely clear to you. So, there comes the load mobilized in the support system, and the other thing is deformation of the support system. How these two are interconnected, that you should always try to explain if somebody asks you what is rock mass tunnel support interaction. Coming to the rigid support system, the load which is mobilized in the support is very high, and the resulting deformation is very small, and so vice versa. So, in case if the resulting deformations are extremely small, these lead to the failure of support system due to yielding of the supports. But in case of the other one, that is when you have very low load which is mobilized in the support and the resulting deformations are very high, in that case the failure is due to the excessive deformation. So, the net result basically is the support system which is neither too rigid nor too flexible. So, remember the quote that I told you when we were discussing NATM. So, there also this particular term came, that neither too rigid nor too flexible. So, because if we go to the extreme sides, this is what is going to happen. Either the failure will take place because of the yielding of the support system, or the failure will take place because of the excessive deformation, and we do not want either of this to happen. So, we have to somewhere be there in the middle of these two extreme situations. Now, the ground response curve is a term that clearly defines the characteristic of the rock mass surrounding the excavation. So, we have seen that when we talk about rock mass support interaction or the rock mass tunnel support system, then in that case we have two components. One is the tunnel or the excavation itself, and the other component is the support system. So, the characteristic of these two components are given by ground response curve and support reaction curve. Ground response curve gives us the idea about the characteristic of the rock mass which surrounds the excavation, and the support reaction curve, it defines the characteristic of the support system. Now, to understand these in a better manner, let us take few cases of different rock types, and first let us discuss a two-dimensional situation which will not be there in the field, but this I am discussing with you just to make sure that you first understand the concept of the rock mass tunnel support interaction properly, and then we will go to the actual three-dimensional case. So, we take the two-dimensional condition for all the cases that I am going to discuss. So, we take the first case of the competent rock. So, in that case, first of all, let us understand some of these terminology. So, here we are going to define Pi as the radial support pressure. In this case, this curve ABC, see this one, this is the straight line . Why this is straight line? Because we are talking about the competent rock, and this is going to be written as GRC, which is the ground response curve in such case. Then we have the linear elastic deformation in this case, because we are talking about the competent rock, and I mentioned to you that based upon the type of the rock or the type of the support system, you may have elastic, elastoplastic, elastic, plastic, and the time dependent kind of behavior. So, in this case it is the linear elastic deformation where UR is very small, maybe to the tune of 1 to 10 mm. And then you focus on the curve OB, which is again a straight line, and this we call as support reaction curve. So, this line OB is giving us the idea about the characteristic of the support system. So, we have few cases here. So, the first one is if we want to arrest the total deformation of the tunnel periphery so that this radial deformation is equal to 0. So, let us write that to arrest the deformation of the tunnel periphery to a value of UR to be equal to 0. What should we do? We should provide the support system, of course. So, what will be the stiffness of the support system in that case? So, the stiffness of the support system, which I am writing as say K, to be provided will be what? See here, this is say Ks at the point A, because why I am calling this point as A point? Because corresponding to this you can see that UR here is equal to 0. So, KSA is going to be P naught divided by the deformation at the point A. So, what is that deformation? Which is equal to 0. So, this is nothing but UR at A. This is the basic definition of the stiffness, and you see that this is tending to infinity. So, what does this mean? That if we want to completely arrest the deformation, we have to provide very rigid support system, and for all practical purposes the stiffness is very high, and you can consider it to be tending towards infinity. So, what will be the result? That will be very uneconomical support system. Then I take the other case, that is the second one. Now, if UR is equal to UR at B, means here this point. So, if this is allowed, then the required support pressure, what it is going to be? It will be Pi will be equal to Pi at point B. So, you see that here. So, what will be the stiffness of the support system in this case? Which is required is going to be Ks at point B will be equal to Pi at point B divided by Ur at B. And of course, this is going to be a finite value. And we take the third situation where UR equal to UR at C. This means here. So, see practically here, what is the support pressure, radial support pressure? This is 0. So, if this is to be allowed, then the required support pressure will be Pi, which is equal to Pi at point C. And what is Pi at point C? This is equal to 0. So, we will have the stiffness of the support system apply the expression which is required, of course. So, that is going to be Ks at C will be equal to Pi at C divided by Ur at C. So, Ur at C is some finite value, but since Pi at C this is tending to 0, so this will become equal to 0. So, you see that we have the competent rock and 3 situations in case if you want to arrest the complete deformation, which is represented by this point A, and in case if you want to allow the maximum deformation such that the support pressure is 0, which is another extreme, that is point C, and another point B which is somewhere in between, and therefore you will have the finite value of the stiffness of the support system. So, this is how we can find out for the competent rock. Let us take the next case of the competent rock, but it has relatively lesser value of modulus and the behavior is non-linear elastic rock. So, how does this look like, the behavior? Let us take a look here. So, again on x-axis we have the radial deformation and on y-axis we have the radial support pressure. Say here of course you have Pi, and here this is where you want it to be completely arrested, all the deformations, it is 0. So, since it is non-linear elastic rock, so how it is going to be? in the beginning we will have some linear response, and then beyond that it becomes nonlinear. So up to this much point here, this is what is your linear response, and beyond this you have the non-linear response of the system. Of course, here you have Pi, which is let me write it here. Pi is the radial support pressure. And then let us say I take this point. So just join this point with the origin, and I take maybe one more point here. So let us say that this point is point A, this is B, this point is C, and this point is D. So I will just drop a vertical line from point B and from point C. So this is going to be UR at C, this is UR at B. This is of course the origin. So the stiffness here is going to be the slope, of course. So this I will write as Ks at B, and similarly here we will have Ks at C. Then here this is the GRC, that is ground response curve in the absence of any support system. So this we know that because it is the competent rock, but it is having a relatively lesser value of modulus, and therefore it shows a non-linear elastic behavior. So this is how the GRC is going to be. So in this case UR is larger than the previous case, which was case 1. So in this case maybe it is of the order of say 50 to 60 mm, and in this case we have the in situ stress to be less than yield stress of the rock. So this condition is there. So depending upon what is the deformation that is allowed, accordingly you can find out the stiffness. You see that the more the deformation which is allowed, less is the stiffness of the support system which is needed. So here you see that at point D, it is UR at D which is very large, corresponding to which the support pressure which is needed is 0. So in this case this may be to the tune of say 50 to 60 mm, and it is larger than the previous case of the competent rock. Then we can have the third case where we have incompetent rock with P0 greater than the yield stress of the rock. So let us take a look at how its GRC and support reaction curve will look like. So here we have UR and radial support pressure Pi on this axis. So here we will have in the beginning some linear portion, and then the non-linear elastic deformation. Then we will have the plastic deformation. So say this point is A and say this point is B, which is the linear elastic deformation, and then up to this point, say this is point C, you have here as the non-linear elastic deformation, and beyond this you have the plastic deformation. So, corresponding to this point B, maybe you have here you are at B, then corresponding to the point C, you have you are C. And say if I take another point here which is D, and in this case you are at B is allowed. So, corresponding to this we have you are at D. So, its stiffness is written with a little bit different notation, that it is Ks at D when the deformation at B is allowed. So, this is how its behavior is going to be. Now, let us try to understand some of the values here. So, basically here this point I will mark as E. So, basically here A, B, C, D, E is giving us the idea about the ground response curve. You are at B is much less than you are at C, and even you are at C is much smaller than you are at E. You are at E is pretty large deformation. So, we have this stiffness, that is Ks at D when the deformation at point B is allowed. So, how are we going to do that? See, Pi at D, this is going to be equal to this divided by U R at D minus U R at B. Now, if you have this U R at E more than the permissible deformation, so what will happen? There is going to be the collapse because of the excessive deformation. So, in this case, this loosened rock around the tunnel periphery may collapse into the cavity. So, this is how, by looking at different types of rock, we can explain that how the stiffness of the support system can be determined if you have to completely restrict the deformation, or if you allow some deformation, then how we can get the stiffness. So, this was all about the two-dimensional condition, and here I tried to explain you that how the stiffness and the deformation, stiffness of the support system and deformation of the rock mass, how they are interdependent on each other. So, now in the next class we will try to understand the same concept, but with the help of a three-dimensional problem, which is more close to the real situation, field situation. Thank you very much.